So, hello student, welcome. Today we will learn something called the short-term behavior of a Markov chain. Okay, so far we have discussed about the long-term behavior. For example, the steady-state probability. These are part of long-term behavior. So in short-term behavior, the most important thing what we are going to learn is called the absorption probability. So absorption probabilities. Okay. Yeah, so what do you mean by absorption probabilities? So now recall that. So let me give with an example. So this example I discussed earlier also. So suppose we have this kind of Markov chain with 5 states, and these are the transition probability curve. And say this. Okay, and kind of this. Okay. Now you call that the state 1 and 4, 5, they are recurrent state. In fact, this 1 will be a single class. So A1, this is a single class consisting of only one state. Similarly, A4 or A5, they are the one class and they consist of 4 and 5. Okay, and 2 and 3 are transient states. Okay. So the question is that if you start with anywhere, so for example 2, eventually what happened? Eventually you will ended up with 1 or 4. The moment you ended up with 1, you will always coming. You will be inside 1, right? You cannot go outside 1. So that means what? This means that the state 1 is absorbing me. Okay. Similarly, if you ended up with 4 or 5, whatever, they are a simple single class. So they will also play the same thing, and you cannot come out from this class consisting of 4 and 5. Okay, so for this our study, we will consider the full class as a kind of a set, or you can think kind of 4 or 5 is an this is so they have the same class of 4 or class of 5, right? The current class of 4 and 5. So they are kind of representative of the same class. Okay. So the question is that what happened. Okay, so let me define then this. So we say FD recurrent class is a observing is a so okay, so observe not FD, so I should say right now this. So I can write down FD, no problem. It's an observing set, observing state. Okay, so what does that mean? That means the probability that you go you suppose you are inside K, this is 1. Okay, so K is recurrent state, or this is for single state. State consists of single state, or representative, you can say that representative of a recurrent class. Okay, so once you are inside K, you will be always inside K. This is probably this one, right? And if you are outside, if you want to go to outside, this is 0 for all J not belongs to the class of K. Okay, if j is outside the class of k, then probability that you go to k to j is 0. Okay, so this is called the recurrent state. Sorry, observing state. Now, if suppose if there is only one say, class, okay, for example, okay, so if there is only one class, uh, so you start with say 1 and then 2 and 3, okay, and there is only one observing class, one recurrent class. So eventually you start with a 2 or 3, whatever, doesn't matter, you will end up with a, right, 1 always. But problem is that if there are say 2 observing class, then question is that if start with something say 2 or 3, whether you can go to 4 or 5, 1, under which probability, what is the probability that you can go to 4 or 5. Okay, so this thing we need to study properly. So then let me define it some symbols. Say my symbol is there. So suppose I am defining a is, this is the probability that xn eventually, so the number eventually becomes equal to the observing state. So I already defined the observing state means, so this is kind of representative of a class, okay, is given that you start at say I state, okay. So from I state somewhere, with what is the probability that it goes to 1 is equal to 1 or is equal to 4. This is my probability. Then what happened? Then so the question is that can you calculate this kind of absorption probability equations? So absorption probability equations. Okay, yeah. So yes, obviously. So let S be an absorption state. Okay, then obviously the way I define AIS. So if I want to find out ASS, so that means if I starting with say S, what is the probability I will be always S? That is always 1 SS. Okay. And what happen if I start with somewhere outside S? So this is 0 for all I which is not belongs to that class of S. Okay, or for the time being you can assume that S is a single recurrent class consisting of only one state, then you can say that I not equal to S. Okay, in this case. Next thing is important, what happens from other state. Okay, so if I is a transient state, then what happens? Transient state, then what? Okay, then what happens? So what does that mean? That means for my first example, let me draw again. So let me solve this by example, and then I will give you the general solution. uh, Suppose this is my diagram and this, okay. So suppose you start with 2, you want to know that what is say a2 and say 4. 4 or 5 they are same actually, because they are the single class. Okay, so if you want to find out these symbols, so you want to know that what happened, what is the probability that from 2 you will end up with 4. Okay, so so now suppose you know the probability here, so you know this probability p, this is 2 3. Okay, and then this is p 3 2, and then p 2 1. Okay, and then p 3 4. Okay, so so from 2, if you start at 2, then you have two options. Either you can go to 1, either you can go to 1 with probability p1 2, or you can go to 3 with probability p2 3. Now once you are inside 1, and then you can ask what is the probability that you are going from 1 to 5. So you can write down either p21 into from 1 to 4. So this is a14 probability that you are going from 1 to 4, plus the other part, total probability theorem you can use, p23, and you ended up with 3, right? When you go from 2 to 3 with probability p23, you ended up with 3, and you are asking what is the absorption probability from 3 to 4. So this is a34, right? But you know that a14 is 0, because 1 is also absorbing state. So in this case, this will be um, in this case this will be p23 a34. Okay, okay, yeah, a3. And okay, so and also you can ask what happened uh, when you start at 3. So if you start at 3, so if you start at 3, then what happened? Then you can either go to 2 or you can go to 4. So from 3, absorption probability will be what? 3 to 4. So either you can go to 3 to 4 with probability p34. So p34, and then you are at 4, so the absorption probability will be a 4 plus you can go to 2 with probability p32 into absorbing probability 2 to 4, right? From 2 to 4, what is that probability? And you know that this is 1, so the answer will be p34 plus p32 into p34, right? Now you can understand that there are two unknowns here. Okay, two unknowns are what? A24 and A34. So, and two equations, so two unknowns, there are unknowns, and two equations. Equation 2, and then you have equation 1 here, and you can solve these two equations to get the final answer, right? So, so this is the I will I'll give you the general result. So this is the kind of example. So in general, what happens? So let me define it. So um, so in general, the proof. Okay, so the proof goes like this. Okay. So let I be a transient state, and A be the event that this state S is eventually reached. Okay, clear? So you start with I and then you will reach S, and this event is A. So we have a IS probability such that you will have reached S, given that your starting point is I, it's not equal to I, right? Now you can use total probability theorem. Now using total probability theorem, what you get. So what you can do, you can either see here, you see the example, you can go to the neighboring state. The short term probability tells you that you can go to 1 or 3, right? Same thing here, you can go to any jth state from I, and then you can write down this probability as probability A such that x1 equal to I and then x1 equal to j, right? And then from j to from x1 equal to j into prob, right? So this probability you can write down sum over these probabilities. This is using total probability theorem. Probability theorem we already learned in the class. Okay, and now you see that obviously we know what is this probability. Sorry, this is I. This is I. Okay, yes. So this you can write down as j equal to 1 to m probability of A. But you know that in Markov chain only the last one does matter, so this does not matter. So this will given that x1 equal to j, okay, and then this is nothing but p. From I to j we are going, so pij. Clear? But what is this? So this is tells you that you want to reach the state S such that you are at state J, and this is by definition AJS, right? So this is you can write down sum over j equal to 1 to m Pij, and then this is AJS. Clear? So thus what you can do, you can write down AIS is sum over j equal to 1 to m AJ P, sorry, we write down probability first, so you can remember easily Pij into AJS, and this is very important formula for calculating our probabilities in the problem. Okay, so now let me calculate. So one example, so it's a small example. Suppose we have this kind of graph 1, 2, 3, and suppose that this is 0.2, this is probability 1, and this one is 0.4, 0.02, 0.3. Okay, and yeah, 0.3 to say 4, and this doesn't matter, then again I am writing it. So this is 0.7, and then this is 1, this is 0.3, okay, and then maybe this is 0.5. Okay, Now, because you see 4 and 5 are single transient, single recurrent state, so you can club these two together. I can write down this itself single is 1, and then it becomes, so after lumping, you can lump those two things, lumping 4 and 5, this transient probability graph become, so you can write down this graph as 1, and then 2, this is 0.2, and this is 1, and then from here to here 0.3, here to here 0.4, okay, so I think there was one more here, 2, 2, 4, yes, 0.1, and then the 4 and 5 you lump to one state, say 6, and then you are going to, you recall that from 3 you can go by 0.5, and then from 3 here you can go to 4.3, so 0.3, 0.5 will become 0.8, so the new graph here it will be 0.8, because 4 and 5 will now become a new state, okay, and here you will have 1, but from 2 you can come to 6, it's 0.1, okay. So here you want to find out what is, say, A26, okay. Now A26 is what? So A26, either you can go to 1 here, 0.2, and to A. So the moment you are inside A, so you want to know what is A16, okay, and you can stay here at 2 with 0.3 probability, and then the same thing to 6, but you can go to 3 also, so it is with 0.4 probability, and then you are asking, the moment you're inside 6, you want to know what is the absorption probability from 3 to 6, okay, but this one A16 is 0, because A itself is the absorption state, so this get cancelled, so the answer is A26 equal to 0.3 into A26 plus 0.4 into A36, right? And finally, what you will get? Finally, so this is what? So after calculating, this is 0.7 A26 is equal to 0.4 A36. Okay, and obviously 1 minute. So, or you can go to, yeah, no, you can go to 6 also. So A plus 0.1 into A66, right? So A6 is equal to 1, so 0.1. This is 1. This symbol is 1. Okay, so this is this plus 0.1. This is one equation, and second equation is what? Second equation, you want to know what is A36. Now from 3, either you can go to 2 or you can go to 6. There are two options only. Now you can go to, so you can go to 2 with probability 0.2. So this is 0.2 into A26 plus 0.8 into A66. Okay, so what does that mean? That means you are inside 6. What is the absorption probability? 6. So this is 1, and then you will have a 2, sorry, 0.2 into A26 plus 0.8. Okay. Now there are two equations in two unknowns. Now you can solve those things. If you solve those things, that final answer will be what? A26 will be equal to 21 by 31, and A36. This is, you can easily solve it. Okay. Now suppose that so from state 2 we are going to 6 finally, eventually, with probability 21 by 31. But from state 2 you can also go to 1, state 1. Okay, state 1, right? So there are two options, because there are two possible absorption states. So you can either go to 6 or 1, and those two are complementary. So you can obviously find out A21 is nothing but a complement of this, which is 10 over 31, and A31, it is equal to 31. Okay, clear? So with that discussion, what you understand? You understand that. So remark. Okay, so suppose, so you write down, say uh, you said something, say lambda be the collection of um, distinct representation of recurrent classes so that is what, that is lambda collect all those s such that uh, this is so this is s, collection of s inside that state space. Okay, but no to this, or rather you can write down like this mathematically. I think you can write down this kind of s1 s2 something, say sk. Okay, such that um, SIs are recurrent state with ASI not equal to ASJ for all I not equal to j. Okay, so they are distinct representative, and then if you sum over all those s belongs to lambda, then you can find out that it doesn't matter from where you start, sum over s, this will be always 1 for all I inside series. Okay, clear? And this is also the important formula to calculate our probabilities. Okay, so this is kind of short-term behavior, that when you start with the state, what is the next step you go, and then with that you use a recurrent formula to find out the absorption probability. Now, one of the very famous example of this solution is called Camel problem, and this is, I already tell you in the beginning of, I think, 3-4 lecture before. Let me calculate this thing in details. So what is gambler win problems? So in the gambling, the gambling game, so you can either win with some certain probability, or you can lose it, right? Suppose you start with some particular, say, I money, and you can either win say 1 rupees money with some probability, say P, or you can lose it with probability 1 minus P. There are two options, and you will finish the game if you, say, ended up with some M money, right, with P. The moment you will ended up at P minus with M, then you will leave the game. So this is probability, say winning probability 1, right? Similarly, you will finish it once you will have 0 money. So once you have 0 money, so you have 2 with P and then 1 minus P, 0 1 minus P. The moment you will, this is a losing state, lose, it's a win. Okay. The question is that if you start with, say, if you start with uh, with I rupees, INR, then what is the probability? What is the probability that eventually you will lose or win? You will losing or winning. So if you know one, then if you know the other one, because they are complementary, right? Clear? So this is a question. So now how do you solve this kind of problem? So solution. Okay, so now I am assuming that my say A is equal to 0, so that means this is my absorption state, so I am ended up with losing. Okay, so if A is equal to 0, then question is that if you start at 0 money, then what will be the probability eventually you have 0 money? Over this is, so once you are 0, then game will be finished, right? So this is 1. Now if you start with say M money, and then it is always 1, because when you are already M money, then you will not play the game. So this is the assumption already, you know. My interesting part is that in between what is the part is there. What about if you start with money I and you will end up with S? S means 0, so this is my 0. Okay, and from this equation, so let me find out the equation. Yeah, so this equation, so AIS equal to summation PIJ EJS, J over 1 to M, right? So AI0 is what? It is summation, so PIJ summation, okay, so J equal to whatever, doesn't matter, Pij and AJ0, S is 0, right? So so what does that mean? That means so from I state either you can go to I minus 1 state when you lose, and that probability of losing is P minus 1, which is Pij here. So this is A I minus 1 comma 0 plus, you can win also, you can go to, with probability P you can go to the next state, I plus 1 comma 0, right? And this is true for I equal to anything in between 1 to M minus 1. Once you are in M state, you will leave the game, you will win, right? So you leave the game. Now how to solve this kind of equation? So let us solve this kind of equation. So let me write down this equation as of this form. So you see this equation, you can rewrite it as 1 minus P times A I minus 1 0 to A I 0 to P times A I 0 A I plus 1 0, right? Yes, so now I'm writing, so I'm writing, say delta I is my A I minus 1 0 to say A I, rather A I 0 In general, let me write down AI 0, I plus 1 is 0. Okay. So then if I use these symbols, then what happens? Then this equation becomes 1 minus p times delta I minus 1, right, equal to p times delta I, right. Now again I am writing another symbol, say my rho is equal to 1 minus p by p, and thus uh, this absorption probability equation is what? Delta I equal to rho times delta I minus 1, right. This is new recurrent relation, clear, and this is true for I equal to 1 to n minus 1. Okay, and using the mathematical induction you can easily find out that now using mathematical induction we have delta I is nothing but rho power I into delta 0, and this is true for I equal to 1 to n minus 1. Okay, clear. Now what is the sum of, now note that the sums, so delta 0, delta 1 plus delta m minus 1, because we still define for n minus 1. If you sum it up, then what happens? See, each delta is difference between ai and ai plus 1, right? So if you sum these things, then you'll have, and then they get cancelled, right? So you'll have a0, so a0 0 the initial state, and a m0, right? Now a00 is 1, because whenever you are inside 0, so obviously you end up 0, but am0 equal to 0, this portion is 0 and this is 1, so this answer is always 1, right? The sum of these things is 1, and done. So this sum is 1 means what? You just replace the value of delta I in this equation, and they will get something in terms of rho power I. Okay, so thus what you have? 1 plus rho square and dot 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 rho power minus 1 into delta 0 equal to 1, right? So I just substitute the value of delta I inside the above equation, and then I will get this thing, and this implies that my delta not equal to two possibilities, either 1 minus rho. This is geometric series, so either this, if rho not equal to 1, or if rho equal to 1, then it is 1 1 1, so there are n many choices, so this is 1 by n if rho equal to 1. Okay, clear. So now if we, the moment I know the value of delta, so I know value of other thing also. For example, then I can say what is the value of delta I. So delta I, for each I it will be rho power I into delta naught, but delta naught is what? This is delta naught is this, if rho not equal to 1, and 1 by m if rho equal to 1. Okay, so I already got delta i's, but delta i's are different between these absorption probabilities, so you can also find out the absorption probabilities. So finally what we have, then ai can write, we can write down ai is what? I mean ai is equal to what? ai 0 0 minus delta minus 1, right, delta I minus 2, and so on, and last one is delta 0. And if you substitute this value, then you have 1, this is 1 minus rho I minus 1 plus rho I minus 2, and the last one is rho plus 1 and delta 1. Okay, again this geometric series, so you have, the answer will be 1 minus rho I by 1 minus rho, and delta naught, but delta naught is what? Delta naught equal to 1 minus rho by 1 minus rho power m, right? So this part get cancelled and you have answer 1 minus rho power I divided by 1 minus rho power m if I not equal to 1. Sorry, rho not equal to 1. If rho not equal to 1, then you will have these things. Okay, and if rho equal to 1, then what happens? Then we can find out from here that so if rho equal to 1, then this absorption probability will be what? It will be nothing but, okay, it's all m minus 1 part is there, so this get cancelled, and this will be m minus I by m. Okay, clear? So either you have this 1 minus this, so this is rho equal to 1, and rho not equal to 1 is what? Rho power I minus rho power m by 1 minus rho power m. Rho not equal to 1, right? Because 1 minus this, so 1 minus rho power m, then 1 get cancelled, so this I minus m comes, right? So you get all the absorption probability. So you start with I, and then you will end up with 0 with this probability. Now you see rho equal to 1 means what? Rho equal to 1 means this is kind of uniform kind of distribution, but this is the interesting part. See, when you go to a gambling game, then you see that the probability of winning, um, uh, is less. For example, you have 7 options, you will win if you get only 1 option, right? The probability of winning, that means the P is less than, say, half generally. Now whenever P is less than half, if P is less than half, then what happens? Then 1 minus P over P. So 1 minus P is greater than half, less than half. So this is rho which is greater than 1, right? If M is if P is less than half, probability of winning is less than half, then rho is greater than 1. Now you note that this equation, if rho is greater than 1, then eventually means when M is large, then this probability is going to what? This probability is going to 1. So that means what? That means eventually you will lose with probability 1. So this is, you are going to lose, right? You are going to 0 state. So when if this is this, and let's say m tends to infinity, then what happens? Then ai0 means that probability of you losing, and this is what? So this is 1 minus, so let me p power I, rho power I minus rho power n, 1 minus rho power n, right? So this you can write down as 1 by rho power m times rho power p minus m. This is negative, so 1 rho power m rho power minus m. This get cancelled, right? And then when m tends to infinity, this part tends to 0, this part tends to 0, so this part whole part tends to 1 as m tends to infinity. So what does that mean? That means eventually you are end up with losing. This is very clear. So this kind of, that's why it's called Camel ruin problem. So you are going to ruin your fortune. You are not going to win it. Okay. And the next question, what is the winning probability? So, and finally, uh, the winning probability is what? Winning probability is, you start with I and end with M, which is nothing but 1 minus I, and start with I and end with 0, right? This is a complement, and thus it will be two options, either 1 minus rho I 1 minus rho power m when rho not equal to 1, or 1 by m, sorry, I by m if rho equal to 1. Okay, and you see that again when m tends to infinity, this tends to 0. So winning probability tends to 0 as m tends to infinity and rho greater than 1. Okay, so you are going to win with probability 0. Okay, so this is kind of a very important example to understand the absorption probability, right? Now question is that one can also ask what happened to expected time, like what is the expected time that you are going to win this, you are going to end up with kind of one of the absorption states. So let me discuss a little bit expected time to absorption. Okay, so now so I don't care with which state. When I'm saying absorption, I mean that state can be anything, any recurrent state. Okay, so now so absorption means absorption absorption state is kind of it's a union of all recurrent classes here. When I want to say expected time, just I don't care differently. So I want to know that what is the expected time that it will ended up with in the one of the absorption class. Okay, so here we define something called mu I. This is expected value, is the number of transition until absorption. Okay, such that you start with I, and then this is mathematically you can write down that this is nothing but expected number of minimum of n, which is at least non-negative, such that xn is recurrent state. State and it's not equal to I. Clear? Okay, so obviously if I is the recurrent state, then mu I equal to 0, because you are inside the absorption set, so you don't need any time, right? And if I is not a recurrent state, okay, so for I transient state, you can use a similar argument to show that mu I is nothing but 1 plus summation j equal to 1 to m Bij for all I which is transient state. This is clear? Because first if you are in I state, you start with I state, you go to you take one move, so you are in I state, you take one move, and then you want, suppose you are end up with J state. Now from here you want to know that what is the expected number, and if the expected number is mu I from here, and then from here this number is mu j, right? So you can go to say anywhere j, k, whatever, and then you have to take sum of all those things. First you need to take one step, so that is 1, and then you have sum of all those. So this is 1, 2, and dot j, m. Okay, anywhere you can do. So thus this is your expected probability of this is the expected time to reach an absorption set. Okay. Yeah. So and I will end up with this problem with one example, and this will be the last lecture of this course. So the example, so this is a called spider and fly example. Fly. So what happens? So you have a spider is sitting somewhere one, something say m minus one and m. So there are spiders sitting here. Okay, here also spider sitting, and you can either so a fly is there in the state 2, 3 and m minus 1. If you ended up with 1 and m, then the spider will eat it. So it's kind of absorb the things, right? So now suppose this is you can go from there to there with probability 0.3, come back from here to here probability 0.3 and stay there with probability 0.4. That is true for everywhere. Okay, 0.4, 1 into the 0.3, 0.3. Then question is that what is the expected time that spider will eventually eat the fly? So fly has to be inside, start with anywhere in between 2 to m. What is the expected probability, right? The if fly is inside 1 or m, like mu1 or mu m, they are already in absorption state. Because they are in absorption state, that is 0, right? Now in between what happened? So in between, if for I for 2, 3 and m minus 1, then what happened? Then mu I, in from our formula, it is 1 plus this probability, right? So from this probability, what you can find? So you have three options. When you are in I, you can either go to with probability 0.3 I minus 1 state, and when you are in the I minus 1 state, say suppose this is I plus 1, I minus 1. So this will be probability 0.3. If you come to I minus 1, then you are asking from I minus 1 what is the expected time, and that is nothing but mu I minus 1. Or you can stay with 0.4, or you can go to I plus 1 with 0.4, 0.3 probability, right? This is the formula. Clear? Now you need to solve this kind of equation to find out the example. For example, if m equals to 2, 3, 5, whatever small number 5 or 6, then you will have those many equations and you can easily solve it. So here you will have, you can see that you have m minus 2, many unknowns with same number of equations. Okay, so thus you can solve for mu i's, and those will be expected probability. Okay, so this is the end of my lecture for this course, and I wish you all guys for a success in your final exam. Okay, all the best to your final exam.